Welcome to this walkthrough of LeetCode problem number 1015, smallest integer divisible by k. In this problem, we explore an interesting challenge involving modular arithmetic and mathematical reasoning. Let's dive in and uncover an efficient solution together. In this problem, you're tasked with finding the smallest positive integer, n, such that a number made entirely of n1s is divisible by a given integer, k. This number is formed by repeating the digit 1 exactly n times. For example, if n equals 3, the number is 111, and if n equals 5, the number is 11,111. Your job is to determine the smallest n for which this number is divisible by k. If no such number exists, you should return -1. The input is a single integer k, which lies between 1 and 100,000, and the output will be the smallest n that satisfies this condition, or -1 if it's not possible. If no such n exists, meaning there's no number made up of n1s that is divisible by k, the output should be -1. Let's look at an example to clarify. Suppose k is 1. In this case, the number formed when n equals 1 is simply 1. Since 1 is divisible by 1, the smallest n is 1. This is a straightforward case where the solution can be determined immediately. Now take another example where k equals 3. Here, we'll test numbers formed for different values of n. For n equals 1, the number is 1, which is not divisible by 3. For n equals 2, the number is 11, which is also not divisible by 3. Finally, for n equals 3, the number is 111, and this is divisible by 3. Therefore, the smallest n in this case is 3. This demonstrates how you systematically test numbers until you find the smallest one that satisfies the condition. Finally, consider the case where k equals 2. Any number made up solely of the digit 1, such as 1, 11, 111, and so on, will always be odd. Since even numbers like 2 cannot divide odd numbers, it's impossible to find an n where the number is divisible by 2. Hence, the output is -1. It's important to consider edge cases like this. For example, when k equals 1, the solution is always 1 because any number can be divided by 1. On the other hand, for k equals 2 or any even number, the output will always be -1 because numbers made entirely of 1s are odd. Additionally, for large values of k, the solution must remain efficient, and for prime numbers, the algorithm needs to carefully check divisibility. The goal is to ensure the solution handles all cases correctly and terminates efficiently when no solution exists. To solve the problem of finding the smallest integer n such that the number formed by repeating the digit 1 exactly n times is divisible by k, we explored several approaches. The first approach, brute force, is intuitive but highly inefficient. Here, we generate the sequence of numbers 1, 11, 111, and so on, checking divisibility by k at each step. While this approach directly tackles the problem, it quickly becomes computationally expensive because the size of the generated numbers grows exponentially with n. This not only increases the time complexity but also leads to significant memory usage when constructing large numbers. As a result, brute force is not feasible for large values of k. To overcome this, we considered an optimized modulo approach. The key insight here is that instead of constructing the full number, we track only the remainder when dividing by k. This allows us to iteratively calculate the remainders using modular arithmetic, avoiding the need for large number construction. Additionally, by monitoring remainders we've seen before, we can detect cycles, which tell us if no valid n exists. This approach is a significant improvement over brute force in both efficiency and scalability. Now, an important observation in the optimized modulo approach is that the remainders are always bounded by k. This is because there are at most k unique remainders possible when dividing by k. If at any step we detect a repeated remainder, it means we've entered a cycle, and no solution exists. In this case, we return -1. However, if the remainder becomes 0 at any step, we know the corresponding n is our solution since the number formed by repeating 1 exactly n times is divisible by k. The time complexity of this approach is O(k), as we only process a maximum of k unique remainders before either finding a solution or identifying a cycle. The space complexity is also O(k), used to store the remainders we've seen. Another variation of this approach is the mathematical insight with modular arithmetic. It builds on the same optimized principles but focuses more on the theoretical bounds to further minimize redundant calculations. However, both approaches are fundamentally similar in essence, relying on modular arithmetic to efficiently track remainders without constructing large numbers explicitly. The chosen strategy to solve this problem is the optimized modulo approach with remainder cycles. It provides an efficient and reliable solution by completely avoiding the pitfalls of constructing large numbers. Instead, it leverages modular arithmetic to solve the problem in linear time relative to k. There are several reasons why this approach stands out. First, it's efficient, with a time complexity of O(k), which is optimal under the given constraints. In contrast, the brute force approach has exponential time complexity due to the growth of the constructed numbers. Second, it is simple to implement, directly addressing the problem requirements without unnecessary overhead. Third, it scales well for large values of k, as it avoids explicitly generating massive numbers. Finally, it ensures correctness by systematically tracking remainders and detecting cycles, guaranteeing an accurate result, whether it's the smallest n or -1 if no solution exists. These factors make the optimized modulo approach the most practical and effective choice for this problem. When comparing the different approaches, the advantages of the optimized modulo approach become clear. Brute force, while intuitive, is computationally infeasible for large values of k due to the exponential growth of the constructed numbers. On the other hand, the optimized modulo approach avoids this by working directly with remainders, making it far more efficient and scalable. When contrasted with the mathematical insight approach, both are similar in their reliance on modular arithmetic and their ability to avoid large number construction. However, the mathematical approach places more emphasis on theoretical rigor, whereas the optimized modulo approach achieves the same results with a simpler and more straightforward implementation. This balance of efficiency, scalability, and simplicity makes the optimized modulo approach the ideal solution for solving LeetCode problem number 1015. To solve the problem of finding the smallest positive integer n such that a number composed of n1s, like 111, 1, is divisible by k, we start by understanding the structure of this number. Mathematically, the number can be expressed as 10 to the power of n1/9. For it to be divisible by k, the condition 10 to the power of n1/9% k equals 0 must hold. Simplifying further, this means 10 to the power of n1% k equals 0. However, directly calculating powers of 10 for large n is computationally expensive. Instead, we use modular arithmetic to simplify our calculations. By focusing on the remainder of the number modulo k as we simulate appending ones, we can avoid constructing the full number. Starting with a remainder of 0, we repeatedly update the remainder using the formula remainder equals remainder *10 plus 1% k. Once the remainder becomes 0, we know we've found the solution. If n exceeds k, we terminate the process to prevent infinite loops, as we'll discuss shortly. If we don't find a solution within k iterations, it implies no such n exists. This is because there are only k possible remainders, ranging from 0 to k1. If a remainder repeats, we enter a cycle, meaning further iterations will produce the same sequence of remainders. This ensures the algorithm terminates efficiently. Modular arithmetic is crucial here because it allows us to work with small numbers while preserving the divisibility conditions, making the approach scalable even for large k. Additionally, cycle detection is naturally built into the algorithm due to the bounded range of remainders. This guarantees that our solution either finds the smallest n or determines that no solution is possible in at most k iterations. The time complexity of O(k) reflects this limit, ensuring optimal performance. The algorithm primarily relies on integer variables to track the current remainder and the count of iterations, n. These are sufficient because the problem revolves around modular arithmetic, which only involves small numbers. Optionally, we could use a set to explicitly track seen remainders for cycle detection, but this is unnecessary since the algorithm inherently guarantees termination within k iterations. The detailed steps of the algorithm are as follows: initialize remainder to 0 and n to 0. Then, enter a loop that runs while n is less than or equal to k. In each iteration, increment n by 1, update the remainder using the formula remainder equals remainder *10 plus 1% k, and check if the remainder equals 0. If it does, return n as the result. If the loop completes without finding a solution, return -1, indicating no such n exists. Let's walk through a couple of examples to see the algorithm in action. For k equals 3, we start with remainder equals 0 and n equals 0. In the first iteration, we append 1, giving a new remainder of 0 asterisk 10 plus 1, %3 is equal to 1, with n equals 1. In the second iteration, we append another 1, resulting in remainder equals 1 by 10 plus 1, %3 is equal to 2, with n equals 2. In the third iteration, we append one more 1, and this time the remainder becomes 2 by 10 plus 1, %3 is equal to 0. Since the remainder is 0, the smallest n is 3. Now for k equals 7, initialize remainder equals 0 and n equals 0. In the first iteration, the remainder becomes 1 and n equals 1. In the second iteration, it's updated to 4, with n equals 2. In the third iteration, the remainder becomes 6 and n equals 3. Finally, in the fourth iteration, the remainder becomes 0, so the smallest n is 4. These examples illustrate how the algorithm efficiently finds the solution or determines that no solution exists. Analyzing the complexity, the time complexity is O(k), because we perform at most k iterations to either find the smallest n or conclude that no such n exists. The space complexity is O(1), as we only use a few integer variables to track the remainder and iteration count. Let's also consider some edge cases. When k equals 1, the smallest number composed of ones is simply 1, so n equals 1. For k equals 2, the number 111, 1 is always odd, meaning it can never be divisible by 2, so the result is -1. For large values of k, the algorithm remains efficient thanks to modular arithmetic, which avoids constructing large numbers and works entirely with remainders. This ensures the solution is both optimal and scalable. This code solves the problem of finding the smallest positive integer n such that a number composed of n1s, denoted as 111, 1, is divisible by k. We start by observing that if k is even or ends with 5, it is impossible for any number made up of only ones to be divisible by k. This is because such numbers are always odd and do not end in 0 or 5. Thus, we return -1 immediately in these cases. Next, we initialize remainder to 0. This variable will store the remainder of the division of a number composed of n1s by k. By iterating from n equals 1 to n equals k, at most k iterations, we construct the number composed of n1s dynamically using the formula remainder equals, remainder asterisk 10 plus 1, %k. This formula efficiently computes the remainder without creating the full number, which avoids memory and computational overhead. If at any point the remainder becomes 0, it means we have found the smallest n such that the number composed of n1s is divisible by k, and we return n. The loop is guaranteed to terminate in at most k iterations due to the pigeonhole principle, which states that there are at most k distinct remainders when dividing by k. If no such n is found within k iterations, we return -1, as it is impossible for the number to be divisible by k. This ensures the solution is both correct and efficient, with a time complexity of O(k). This is the Java implementation for LeetCode problem number 1015, smallest integer divisible by k. The code mirrors the logic of the Python implementation, ensuring the same functionality. Key differences include explicit type declarations, the use of a for loop with a defined range, and Java's modular arithmetic for updating the remainder. The solution uses the pigeonhole principle to limit iterations to at most k, ensuring efficiency. In this problem, we're tasked with finding the smallest positive integer composed entirely of ones, such as 1, 11, 111, and so on, that is divisible by a given integer k. If no such number exists, we simply return -1. To solve this, we use a few key observations. First, numbers consisting entirely of ones can be represented as a sequence. Instead of constructing these numbers explicitly, which can get very large, we can apply modular arithmetic to track the remainders when dividing these numbers by k. This allows us to determine divisibility without directly building the full number. Additionally, if k is divisible by 2 or 5, we can immediately return -1, because no number composed of ones will ever be divisible by such k. This is due to the fact that all numbers made entirely of ones end in the digit 1, making them inherently incompatible with these divisors. To implement the solution, we simulate the sequence of numbers using a loop, compute remainders efficiently, and stop once we find a remainder of 0, which indicates divisibility. If we iterate k times without finding a solution, the pigeonhole principle guarantees that remainders will start to repeat, so we can conclude it's impossible to find such a number and return -1. Let's explore an example where k equals 3. We begin by initializing the remainder to 0. Since k is not divisible by 2 or 5, we proceed with the computation. In the first iteration, we calculate the new remainder as remainder *10 plus 1 % k, which becomes 0 *10 plus 1 % 3. This simplifies to 1, so the remainder is now 1. In the second iteration, we update the remainder using the same formula, 1 by 10 plus 1 % 3. This gives us 2. Finally, in the third iteration, we repeat the process, 2 by 10 plus 1 % 3 equals 0. At this point, the remainder is 0, which means we've found the solution. The smallest number composed entirely of ones that is divisible by 3 is 111, and its length is 3. Now let's consider the case where k equals 7. Again, we initialize the remainder to 0 and confirm that k is not divisible by 2 or 5, so we can proceed. In the first iteration, the remainder becomes 0 *10 plus 1 % 7, which equals 1. In the second iteration, we compute 1 by 10 plus 1 % 7, resulting in 4. The process continues with the remainder being updated to 6 in the third iteration, 5 in the fourth, and 2 in the fifth. Finally, in the sixth iteration, 2 by 10 plus 1 % 7 equals 0, meaning we found a solution. The smallest number composed entirely of ones that is divisible by 7 is 111,111, and its length is 6. Finally, we examine the scenario where k equals 2. In this case, we immediately notice that k is divisible by 2. This means no number made entirely of ones can ever be divisible by k, because such numbers always end in the digit 1, making them odd. As a result, we return -1 without performing any further calculations. To summarize, the solution leverages modular arithmetic to efficiently track remainders, avoiding the need to construct large numbers. The pigeonhole principle guarantees that we only need to check up to k iterations, and special cases for divisors like 2 or 5 are handled upfront to optimize the process. To analyze the time complexity of this problem, we start by understanding the constraints of the input, which is a single integer, k. The algorithm's main component is a loop that runs a maximum of k times. This upper limit is established by the pigeonhole principle, which guarantees that there are only k possible remainders when dividing by k ranging from 0 to k1. If a solution exists, it must be discovered within these k iterations. Within each iteration, the key operation involves updating the remainder using the formula, remainder *10 plus 1 % k. This calculation consists of a multiplication, an addition, and a modulo operation, all of which take constant time. Therefore, each loop iteration is O(1). Multiplying this by the maximum of k iterations, we arrive at an overall time complexity of O(k). Now, let's examine the different runtime scenarios. In the best case, the remainder becomes 0 after only a few iterations, meaning the algorithm terminates earlier than k iterations. However, even in this case, the time complexity is still expressed as O(k) in terms of big O notation because we focus on the upper bound. In the average and worst-case scenarios, the algorithm may have to go through all k possible remainders before arriving at a solution or concluding that no solution exists. This confirms that the time complexity remains O(k), regardless of the case. Moving on to space complexity, the main factor is the memory used by the algorithm. The only variable requiring storage is the remainder, which is a single integer. This takes constant space, or O(1). Additionally, the loop counter variable n is also a constant and does not contribute to asymptotic space complexity. Since the algorithm does not rely on any additional data structures such as arrays or hash tables, all calculations are carried out in constant space. With that, the total space complexity of the solution is O(1), dominated by the single variable used to store the remainder. When comparing this to a naive approach, the efficiency of the current algorithm becomes even clearer. A brute force method might involve explicitly constructing numbers made up of n1s like 1, 11, 111, and so on, and checking each for divisibility. This approach has significant drawbacks. Constructing each number takes n space, and performing modulo operations on these large numbers also grows in complexity as the number of digits increases. This results in an overall complexity of n squared, or worse. By contrast, the current algorithm avoids these inefficiencies by working directly with remainders. This eliminates the need to construct large numbers, reducing both time and space usage. By leveraging modular arithmetic, the algorithm achieves k time and 1 space, making it far more efficient than the naive approach. Finally, the mathematical reasoning behind the k time complexity is rooted in the pigeonhole principle. This principle ensures that there are at most k unique remainders when dividing by k. If a solution is not found within k iterations, it means the remainders start repeating, guaranteeing that no solution exists. This inherent limit on the number of iterations proves the algorithm's time complexity is k. To summarize, the solution achieves a time complexity of k and a space complexity of 1. It is an optimal approach to the problem, utilizing mathematical insights to avoid constructing large numbers and minimizing both time and space usage. This efficiency makes it particularly well suited for this problem, ensuring that the solution is both fast and resource conscious. Let's discuss some common mistakes that can occur while solving this problem. First, when k equals 1, the smallest integer divisible by k is simply 1. This is because any number consisting of repeated ones, like 1, 11, 111, and so on, will always have a remainder of 0 when divided by 1. Missing this edge case can lead to unnecessary computations or incorrect results. Next, using a brute force approach to generate the actual number 111, for increasing values of n and checking divisibility is highly inefficient. This can result in integer overflow as the number grows exponentially and wastes computational resources. Instead, leveraging the modulo operation allows you to work with remainders directly, avoiding the need to construct large numbers. Additionally, it's critical to account for cases where k is incompering with 10, for example, if k shares factors like 2 or 5 with 10, no such number is divisible by k. Failing to return -1 in these situations can lead to infinite loops. You should also be mindful of how you calculate remainders. Instead of recalculating the full remainder for each step, apply the formula *10 plus b mod k equals a mod k *10 plus b mod k. This leverages modular arithmetic to reduce redundant computations. Finally, skipping cycle detection in remainder calculations can lead to inefficiency. Since the remainder modulo k can only take values between 0 and k1, any repetition indicates a cycle, and continuing further becomes unnecessary. Now, let's look at some interview insights related to this problem. This challenge is an excellent opportunity to showcase your understanding of modular arithmetic and number theory. For example, you can explain concepts like coprimality and why they matter in determining whether a number divisible by k exists. It's also important to emphasize the efficiency of your solution, highlight how the modulo operation helps avoid constructing large numbers, which is crucial for handling tighter constraints. Be prepared to discuss edge cases such as k equals 1, where the solution is straightforward, and cases like k equals 2, where no solution exists. Additionally, demonstrating your ability to detect cycles in remainder calculations can show your interviewer that you've thought deeply about avoiding infinite loops or redundant operations. Beyond this specific problem, you can also connect it to related challenges. For instance, problems like LeetCode number 7, reverse integer, and LeetCode number 9, palindrome number, share themes of handling integers and digit patterns. Similarly, LeetCode number 233, number of digit 1, and LeetCode number 400, nth digit, involve analyzing or constructing digit sequences, making them conceptually related. Let's explore some alternative approaches and their trade-offs. One method is to use cycle detection with sets. By storing all previously seen remainders in a set, you can efficiently detect when a remainder repeats, which indicates a cycle. This ensures the algorithm terminates and avoids unnecessary iterations. Another approach, though less optimal, is to use breadth-first search, or BFS. In this variation, you systematically explore numbers formed by appending digits like 1 or 0 to a queue. While BFS can be helpful in certain scenarios, it's less efficient for this problem compared to modular arithmetic. When considering trade-offs, the modular arithmetic approach stands out as the most optimal in terms of both time and space complexity. It avoids constructing massive numbers and relies on concise mathematical properties. However, it does require a solid understanding of number theory, which might be challenging for some. On the other hand, BFS, while less efficient, is more intuitive and can be a good way to showcase problem-solving creativity in an interview, especially if modular arithmetic isn't immediately apparent to you. Balancing efficiency with clarity and demonstrating flexibility in your approach can leave a strong impression during technical discussions. Thanks for joining me on this journey to solve LeetCode problem number 1015, smallest integer divisible by k. We discussed a mathematical approach that leverages modular arithmetic and efficient remainder tracking. Be sure to practice similar problems to strengthen your understanding, and I'll see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!